Why do we learn to draw in isometric? Isometrics are quite lifelike, so they are well suited to communicating ideas spatially. They enable you to draw a plan, an elevation, and an end view. A plan, an elevation, and an end view. So broadly, isometric drawings are all made with horizontal lines that are 30 degrees and all vertical lines remain at 90. The simplest way to learn to draw in isometric is by using a piece of trace laid over a 30-degree isometric grid. This gives you enough guidance to make convincing 3D drawings with the reassurance that if you mess it up, you just put another piece over the top and you can redraw. The process of tracing is very freeing and quickly enables you to make advances from simple to more substantial and challenging drawings. Start by drawing a cube, then a couple of cubes, then begin multiplying the cubes like pixels, so that the tiny boxes provide the simple underlying geometry to construct increasingly more subtle forms. This process is known as additive drawing because you add one shape to another and another and another, and you build forms in a modular way. You draw the framework in blue pencil, then pick out the shape in thin pen, then finish the drawing with a thick pen, outlining the whole shape. The next set of drawings you make can combine additive and subtractive sketching. Subtractive sketching, like it suggests, gives you a way of imagining a shape and then taking part of its shape away. So you draw a blue crate, then you refine the drawing to show the shape you want to remove, then you draw the shape that remains. The rule of sketching is that you start from the general and progress to the specific. This enables you to shift the focus of your attention or change a final sketch while you are making it, if a different result drops into your head during the process of sketching. These orthographic sketches show 4 views of a component. You can assemble the views mentally, or you can begin physically assembling them in a pictorial drawing. It's a good idea to make isometric sketches because they're not merely illustrations. In redrawing these shapes, your understanding of them often grows. The orthographic views are constructed on 10 mm squares, and we can apply these dimensions directly to the isometric grid. The shape has 2 diagonal faces which create inclined planes. We draw these by chopping the corners off the basic cube. You can then begin transferring the depths from the plan and heights from the front elevation. Then bring in shape profiles from the left view. As the 3 views begin to overlap, your 3D drawing begins to emerge. When you think there are no mistakes left to make, ink the drawing in. When you draw without a grid, you follow the same procedure of drawing an isometric module in blue pencil to establish 30-degree lines. Then you can begin to develop 3D shapes with a reasonable degree of accuracy. This is an extension of Isometric Exercise 2.5, and it's to show how to section a shape that has 2 inclined planes. Using the shape as a module, you can copy it simply with trace until you have 3 shapes adjoining each other in a line. We will section the 3 shapes as one along the section line I'm drawing here in the plan. I'm drawing a simple plan of all 3 of the modules here. Then I'm drawing the center of the 3 shapes where I will put my section cut. I'm then making points on the plan where the walls of my shape touch the ground. Then I'm projecting up from these points, and these are the internal walls which are at 90 degrees to the floor. Then we draw the inclined planes from the ground line to the very top of the shape. This gives me the shape of the section cut. As the shape that remains behind the section cut becomes clear, colour in the section cut and draw its shape in bold lines. A quick way to introduce scale into your drawing is to introduce figures. This shape has scale, these two shapes, and each of the figures expresses a height. We see the figures and subliminally change the scale of these boxes. Each of these figures represents a human height which we normally take to be, which is around that height. So we would infer that this overall structure is maybe twice the size of a human, a little bit over. So if that's 1.7, that's 2 times 1.7, 3.4, it's roughly 3.5 meters tall. The world isn't all square, so we need to be able to draw curves. To construct a curve, you begin from a rectangular crate, which acts as a guide for your hand. If you can make a reasonably convincing crate, you have a good chance of drawing credible curves. This is a method of drawing ellipses in isometric sketches using compasses. When you have the isometric squares drawn, use the corners of the squares as the centers for the ellipses of the major arcs. To construct their minor arcs, draw center lines and 2 parallel diagonals across the faces of the squares. The point of intersection with the diagonal running from the bottom to the top of the square is the center for the minor arcs. The second method for constructing isometric ellipses is the ordinates method. And it's so called because we use vertical lines superimposed on a true circle as ordinates to tell us the heights of our circle relative to its center line. So draw a circle on a grid using a compass or a template. Divide the circle into the regular vertical intervals that give you your ordinates. Then transfer these heights onto your isometric grid and freehand the circle in. Once you've seen what the circles look like in isometric and familiarized yourself with their type of distortion, you need to train your eye and hand to sketch them convincingly. This is a shortcut that enables you to use the ordinates method to draw drum shapes from ellipses. Construct an isometric box into which the ellipses will just fit. Make a copy of the ellipse onto tracing paper. You can then place the copy under your master drawing in the correct position and draw the top ellipse. Draw the ellipses, then join their tangents to complete the drum shape. This is a great visualization strategy that engineers can use. It's called a cutaway, or sometimes called a reveal, and it helps show details of what would otherwise be hidden. The engineer has taken away some of the slab here in between. This is an existing filler joist floor. These are the joists in question. This is a lintel over an opening, and these joists are laid on the top, so in section it would look like this. This is the parquet floor. These are the small filler joists, and then underneath there's a larger joist here. And he started the drawing by, first of all, taking away this part of the I-beam back to here, so that it makes a reveal here and here. He's then cut away the existing slab to show us the spaces in between, so you begin to get some idea of those internal relationships displayed very, very graphically, very convincingly, without recourse to any technical drawing. This is a good example of isometric drawing being adapted to visualize a proposal, where the engineer is applying a simple additive and reductive isometric technique. The drawings on the left depict one building rotated to show it from two different viewpoints. The drawings in the middle show the effect of removing two portions of its mass, and the right-hand section shows the building with new structure added. In the top right is the schematic plan, colored to indicate the proposed demolition and construction phases.